All right, welcome to The Explainer. Today we are diving deep into one of the absolute strangest results of Einstein's math. We're going way beyond just black holes and into this kinda looking-glass world of their mathematical twins, white holes and the wormholes that might just connect entire universes.
So let's just start with a puzzle, one that seems to break all the rules. The really weird thing about black holes is that from the outside looking in, you can never, ever actually see anything fall into one. It's a paradox that stumped scientists for decades, including Einstein himself.
Just imagine you send an astronaut on a one-way trip toward a black hole. Now, you'd think, right, that as gravity gets stronger and stronger, they'd speed up, right? Just accelerate like crazy. But nope, that is not what you would see. From your safe vantage point, miles away, that astronaut would actually look like they were slowing down.
And this is where reality just seems to split in two. For you, the observer, the astronaut's clock would appear to tick slower and slower. The light from their ship would get stretched out, getting redder and dimmer. And then, just as they reach that point of no return, the event horizon, they'd just seem to freeze, just suspended right there in time, before fading away completely.
So get this, that means, in theory, a ghostly image of every single thing that has ever fallen into that black hole is still kind of imprinted on its edge. So what is really going on here? How can something be falling in and be frozen at the edge at the exact same time? And how in the world does this mathematical weirdness lead us to parallel universes?
Okay, so here's how we're going to break this all down. First, we'll dig into Einstein's idea of curved spacetime to see why things look frozen. Then we'll look at the very first solution for a black hole and how brand new maps of spacetime revealed its hidden secrets, like wormholes and parallel universes. And finally, we'll ask the big question, could any of this actually be real?
All right, so to figure out this whole frozen astronaut thing, we kind of have to toss out what we think we know about gravity. We need to see the universe the way Einstein saw it, not as some empty box, but as a living, breathing part of the whole cosmic story.
I mean, for more than 200 years, Newton's idea of gravity was the best we had, this mysterious force that just acts instantly across space. Even Newton thought it was kind of absurd. But Einstein had this revolutionary idea. Big things like the sun don't pull on the Earth. Instead, they literally bend the fabric of reality itself, space-time, and the Earth is just rolling along the straightest path it can find in that curved space.
And he boiled this amazing idea down into his famous field equations. Now, the math is notoriously complicated, for sure, but the basic idea is just beautiful. One side of the equation has all the matter and energy, and the other side tells you exactly how space-time bends in response. It's a perfect relationship. Matter tells space-time how to curve, and curved space-time tells matter how to move.
So you're probably wondering, how does this beautiful, elegant theory lead to something so paradoxical? Well, it all started when someone tried to solve these equations for the simplest thing imaginable. And in doing so, they unleashed this mathematical monster that even Einstein refused to believe in.
Okay, picture this. It's 1915. World War I is raging. A German physicist, Karl Schwarzschild, is literally in the trenches on the Russian front, calculating artillery trajectories. He somehow gets his hands on Einstein's new paper, and in just a matter of weeks, he does what Einstein couldn't. He finds the first exact solution, describing space-time around a single ball of mass. And what he sent back to Einstein, well, it blew his mind. The math described a black hole.
But here's the thing. Schwarzschild's elegant solution had a couple of weird problem spots where the equations just went nuts and blew up to infinity. The first was right at the center, at radius 0. This was a real physical singularity, a point of infinite density. But the other one, that one was even stranger. It happened at a specific distance outside the mass, at what we now call the Schwarzschild radius.
See, this outer boundary, it wasn't something you could touch. It was a mathematical line in the sand. It marked the exact spot where spacetime is so warped that to get away, you'd have to go faster than the speed of light. And since nothing can do that, anything that crosses that line, this event horizon, can never, ever get out. Not even light itself.
So for decades, this singularity at the event horizon was a huge deal. The math seemed to be saying that as you got close, time itself would stretch out forever, which means nothing could ever really cross it. A lot of physicists thought this proved black holes couldn't really exist. And the whole puzzle didn't get solved until physicists had a big aha moment. They were just looking at the map all wrong.
The breakthrough really came from a simple analogy. It's like this. Imagine trying to map the entire Earth, but you only have a map of the northern hemisphere. Your coordinate system, your latitudes, they're all positive.
but the math itself allows for negative latitudes. Your map is just incomplete. You're totally missing the southern hemisphere.
So what this all means is that the frozen astronaut at the edge, it's not actually happening. It's not a real physical barrier. It's just a distortion, an illusion created by that particular map of space-time. It's kind of like how Greenland looks absolutely massive on a normal world map. The distortion is in the map, not on the planet itself. So, physicists got clever and they developed totally new kinds of maps, new coordinate systems, to get around this problem. And the most famous of these is the Penrose diagram. It's this brilliant piece of mathematical magic that basically squishes the entire infinite universe onto one single tidy picture. And on this map, all light rays travel at a perfect 45-degree angle. This simple rule makes it super easy to see which parts of the universe can affect other parts. And this is where it gets really wild. This is the power of just looking at things from a new angle. Because once physicists drew the complete map of the spacetime from Schwarzschild's solution, the southern hemisphere they'd been missing, they found something, well, mind-blowing. The math didn't just describe a black hole. Oh no, it described so much more. So on this new, complete map, if you look at where you are and trace back all the paths that light could have taken to get to you, you realize your history actually stretches into a whole new part of spacetime that was completely invisible on the old map. And this new place, it's the exact mirror opposite of a black hole. It's called a white hole. It's a place where stuff can only get out. You can never fall into a white hole. If you were inside one, you'd be shot out into the universe, no choice about it. It's literally a black hole running backwards in time.
But wait, it gets even crazier. When you push the map to its absolute limits, another whole region shows up. An entirely separate, parallel universe just like ours. And the map shows that these two universes are connected. They're linked by something called an Einstein-Rosen bridge, which you probably know by its much cooler name, a wormhole.
I mean, just let that sink in for a second. Black holes, white holes, wormholes, and a parallel universe, all popping out of the very first solution to Einstein's equations. The math is totally sound. But this, of course, leads to the billion-dollar question. Could any of this actually exist in our universe?
Yeah, so bad news for any aspiring interstellar travelers. The answer is probably no. There are three huge problems. First, this whole setup only works for an eternal black hole that's always been there. Real black holes form when stars die, and that whole process seems to stop a wormhole from ever forming. Second, the bridge itself is super unstable. It would snap shut so fast that not even light could make it through. And third, to prop a wormhole open, you'd need some bizarre stuff called exotic matter, stuff with negative energy. And as far as we know, that kind of stuff just doesn't exist. It breaks the rules.
And as this quote really gets at, even though these things are mathematically possible, they seem to be forbidden by the other laws of physics, the ones that govern actual stuff. Basically, the geometry says maybe, but the laws of matter and energy say probably not.
But I want to leave you with this one last thought. For decades, the smartest people in physics, Einstein included, they all argued that black holes themselves were just a crazy mathematical idea that couldn't possibly be real, and they were spectacularly wrong. Today, we've taken pictures of them. So it kind of makes you wonder, doesn't it? What else is hiding in the math, just waiting to surprise us all over again?